Okay, welcome everybody to our weekly seminar series. And today we are very honored to host Dr. Gil Lapid.
Not a doctor yet.
Yet,
Almost.
to be soon, from the Hebrew University of Jerusalem, who is doing his doctorate at the Marine Institute in Eilat, the Inter-University Institute in Eilat. And some short information about Gil. He grew up in Haifa and is currently working in the Institute in Eilat. He received his bachelor degree in geology and environmental sciences from the Hebrew University and a master's degree in oceanography also from the Hebrew University. And his current research focuses on the elemental composition of marine sinking particles and applying uranium decay series isotopes as traces for particle fluxes and sources to the ocean. So, Gil, they came to listen to you, not to me, so the podium is yours.
Thank you. So thank you very much. And like Nicholas said, I'll talk about the uranium decay series as mixtures of particles in the ocean. And sorry, I'll be moving a lot from here to there. Oh, shit. This one also doesn't work.
No. Now it will work.
No? Yeah, I think I'm also not the. Okay. Now it's off. Okay, so maybe I'll be here. So in general, in the global climate system, the ocean is one of the largest carbon reservoirs and heat distribution system globally. And it relies on a lot of interfaces with the air and land. For example, gas exchange with the atmosphere or dust deposition and thank you. And the groundwater discharge or coastal deposition of particles. And a lot of those fluxes and chemical modulation of the ocean happens through particles, all kinds of particles, which we will talk about now. And the roles of particles in general are supply of nutrients to remote oceans. Okay, we don't see it a lot because we're next to a coastal environment, but think about the middle of the Pacific Ocean. What brings the nutrients is mostly dust. And it also supports the primary and export production in the ocean globally. And by modulating biogeochemical cycles, for example, here you can see dissolved cobalt distribution across the Atlantic, across basically the same transect. And you can see where there is more or less cobalt, and that depends on relation to coastal environment or mid-ocean reach. And in the end, those particles also fall down, reach to the sediment, and then we can pick them up and study the past conditions in the oceans. And the sources of particles to the ocean, in our case, can be either lithogenic, okay, dust deposition, fluvial inputs, or lateral transport, okay, from the shelf or slope. And they can be biogenic, okay, all kinds of phytoplankton and other creatures which create skeleton, silicate, or carbonate, and eventually being preyed upon by zooplankton and sea. And there is also eutygenic phases, all kinds of iron or manganese oxides which form in the water, or dissolved compound that can be absorbed onto sinking particles and go down. And the processes which involve particles can be lateral transport, aggregation of small particles that are suspended in the water and then they can sink and remineralize, and absorption and desorption of dissolved phases. And primary productivity, which we talked about, that essentially takes nutrients from the surface water, concentrate them through photosynthesis, and then that's the phytoplankton, which eventually get preyed upon by zooplankton, which excrete fecal pellets that sinks to the bottom. And we talked about that. And uranium decay series. So the uranium decay series is a very useful tool to quantify some of these processes in the ocean. And that's due to several reasons. The first one, as you can see, it has a wide range of half-life. Okay, these are the half-lives from billions of years to several hours. Okay, there is all kinds of half-lives which allow us to to quantify large timescales of processes. And the second reason is that there is chemical differences between nuclei. Okay, for example, uranium is very highly dissolved in seawater, and thorium is very tend to be scavenged, attached to particles that sink or form particles. And it has several applications in oceanography. For example, if we look at protactinium and thorium, so we can use their scavenging intensity, okay, to quantify lateral transport and differences in scavenging. Here we can see an example of radium isotope, which are used to quantify groundwater discharge in coastal environment. So you can see that, for example, here, as the distance from shore increases, radium activity decreases until it reaches some steady state. Another example can be lead isotopes, which we use in the sediment, lead-210. Okay, so it can be used to quantify sediment mixing and accumulation rates. And in this talk, I will focus on the uranium comminution age, okay, which is what I use in my first and second chapters in my PhD. And if we'll have time, I'll also talk about the third chapter. But quickly, what the comminution age means. Okay, so we're looking at uranium-238 that decays into uranium-234 through thorium and protactinium, but we don't care about them for this process. And because of the difference in their half-life, if you look at the particle, this method is to quantify the transport time or the time that has passed on small particles. So if we look at any particle, take, I don't know, a rock from outside here, and you look at the isotopic ratio between the activity of uranium-234 and uranium-238, the activity ratio will be 1. And that's because of the difference in their half-life after about 1 million years. Now, when we see what happens inside the grain, and then, again, it doesn't matter if it's a rock, a mountain, or a clay fine particle, okay, because it's an alpha decay, there is a phenomenon called alpha recoil, by which the daughter isotope, the 234, moves a little bit, so a certain distance in the mineral. And when this happens at the margin of the mineral, the daughter isotope may be ejected outside of the mineral. And when this has happened in grains that are smaller than 50 micron operationally defined, we start to have a decrease in the activity ratio. And this decrease continue over time. So the more time passes, the more depleted activity ratio will get. And this represents, this clock starts ticking when the particle becomes small enough to start losing uranium. And when we think about it, this can be dust particles or marine particles in the water, all kinds of clays or plankton, phytoplankton skeletons. But it records the transport time and the burial time. If we take a core, for example, and we measure it, so it depends where in the core this particle will be, right? If it's very deep in the core, so it will have a lower ratio, but it's not because of the transport time, but it's the transport and the burial time. That's okay. By the way, ask questions if you have, while I'm talking, ask questions. Okay, so now I'll talk about what I'm going to talk about today. So my PhD is divided into 3 chapters. Today I will talk about 2 of them, and if I have time, maybe a little bit about the third. And in the first chapter I'll talk about atmospheric dust as one of the main sources of particles into the ocean. In the second chapter, we'll talk about marine particles, sinking marine particles in the ocean. And in the third chapter, if we'll have time, we'll talk about lateral fluxes from the continental shelf and slope into the marginal ocean that we have here in the Eastern Mediterranean. And I'll start by talking about chapter 1. So in chapter 1, we're talking about uranium isotopes and trace elements distribution in atmospheric dust. And what we'll talk about is what is the chemical composition of dust in different mineral phases, and how can the chemical and uranium isotopic composition reveal the provenance of dust, and what is the transport time of dust in our region, because we don't know that. So a little bit about where we did our work. So we're talking about the Gulf of Aqaba, which is the Gulf of Aqaba and Israel in general. It's here, okay, right between the Sahara and Arabian Desert, okay, in the middle of the global desert belt. And this is where most of the dust, the mineral dust in the world, is being emitted from. So other than that, it's a very arid environment with low anthropogenic influence, okay? So we get mostly mineral dust and not not a lot of anthropogenic dust. And dust in the region, so typical dust load, I'm talking about a lot, right? Here it might be a little bit different, but it's about 20 to 30 microgram per cubic meters. But as you can see here, there are very frequent and discrete dust storms which can last between hours to days. And the dust load can increase to up to 400 microgram per cubic meter or even more. And the grain size distribution is mostly lower than 5 microns, so it's okay. We can use the cumulation age to quantify the transport time. And the general composition is roughly 50% carbonate, 20% quartz, and 30% clay. And here you can see an example of two dust filters. That's how it looks like, that we collected in a lab. And you can see there is different sources, okay, Saharan dust and local dust. And just by the color, you can see that there is difference, right, in the composition. So let's talk about where dust comes from and how does it change. So we talked about dust emitting region, we talked about the global desert belt, but even in the Arabian desert or Saharan desert, it's not emitted homogeneously, okay? There are specific regions that from there dust is being emitted. And especially in the Sahara, those regions usually overlap with desiccated lakes or geographic depression that accumulate a lot of fine particles and mutagenic clays in them, which later become dust. Here we can see an example from the Baudelaire Depression in Chad. And that's one of the largest dust emitting region in the world. Some estimation said that this place is responsible for more than 50% of the global dust. And on each one of these potential source areas has a distinct isotopic and chemical fingerprint according to the conditions in which it was formed. So here we can see neodymium and strontium isotopic composition in the Sahara and Levant area. And that's basically, people went to each one of these places, pick up a sample, took it to the lab, and you see that there is difference in the isotopic composition, which can help us identify the source of dust, also chemical composition. And in addition to that, we also used back trajectory models to try to understand where did the dust that we collect arrive from. So here you can see a dust storm that arrived in the Gulf of Aqaba that lasted a few hours, okay? And you can see how high is the dust load. And that's the back trajectory of this specific storm. So you can see that it collected most of the particles over Egypt and the Sinai Peninsula before it arrived to our region. And we divided our samples into 3 groups, okay? Arabian Peninsula, Sahara Desert, and local samples that sometimes come from Europe and sometimes it's a mix. And we collected both dust from ambient conditions, so not when there was specific dust storms, but also during discrete dust storms to have a very discrete signal of these storms. And each one of those filters have undergone a sequential leaching to extract the main mineral phases: the water labeled phase, calcium carbonate phase, iron manganese, magnesium carbonate phase, and silicate phase. And on each one of these subsamples, we did the chemical analysis in ICP-MS and uranium isotopic analysis in multi-collector ICP-MS in Jerusalem. Now let's talk about the results. So the result shown as enrichment factors over the upper continental crust normalized to aluminum. So basically everything above 1 is enriched, everything below 1 is depleted compared to the continental crust. And the first thing we can see that there is a difference between phases, right? If you look at the calcium, for example, you can see that it's enriched in the carbonate phases. Okay, over there you can see the colors of the different phases, and depleted in the silicate phase. And lead also, for example, titanium is depleted in the carbonate phase. So there is difference between phases, and that's already something. And here we took just the magnesium and calcium enrichment factor and compared it between them. And first you can see the difference between the different phases. Okay, this is the carbonate and the oxide phase are pretty similar, but the silicate phase is very different. And what we did, we compared them to potential source areas in the Sahara and in the Arabian Peninsula and other previous works on dust. And what we saw firstly that if you look at the silicate phase, so you can see that it's very similar in its composition to sources from the central and western Sahara. Well, the carbonate phase is more of Eastern Sahara and Arabian Peninsula. Now, it doesn't mean that the silicate dust that arrived to Eilat came all the way from here and arrived here. It probably stopped in all kinds of places along the way and got mixed with other particles. And to further analyze this, we did a PCA analysis which takes into account not only magnesium and calcium or every set of two elements, but the entire elemental composition that I showed you before. And to those of you who don't know, in short, what PCA does, it takes every couple of variables that we have. In our case, it's enrichment factor of 24 elements, and correlates them. And from that correlation, we have a new axis system that accounts for most of the variability in the samples. And so the result of this is that every sample have PC1 and PC2 values that reflects the chemical composition based on the entire chemical analysis elemental composition that we showed before. And we did this analysis to each one of the phases separately. So first thing you can see here, this is PC1 and PC2, and you can see different distribution in different phases. And more than that, what we discovered is there is clear provenance signal. So sample coming from the Sahara have a specific chemical fingerprint, and Arabian Peninsula have different fingerprint, where the local samples are somewhat of a mix, but there is very clear distinction in most of the phases between the Arabian Peninsula and the Saharan sources. And now we move into the uranium isotopic composition. And what we see, again, we divide it into our source areas, and we see here these are the different samples. And we can see there is difference, right, in the composition of different phases. Let's start by talking about the water level phase, okay, which represents salts and highly dissolved minerals. And we can see that the samples from the Sahara are very similar to seawater composition, okay, of 1.148, and also Saharan samples collected over the Atlantic. And the silicate phase, these orange triangles, are somewhere around 1. Some of them are above 1 in the Sahara Desert, but in the Arabian Peninsula, we have some samples that have very low isotopic composition, similar to Chinese less silicate, which are the best representation we found of silicate dust that people measure the uranium isotopic composition on. Okay, we talked about that. And now let's move in again into the comminution age and how we use it to calculate transport time. So if you don't remember, let me remind you that we're saying the more depleted the isotopic composition, the older is the sample. But how much older? This much older. So the uranium isotopic composition we measure today depends on the initial isotopic composition, which we assume to be 1 in our case, and the fractional loss factor, which is a parameter which encompasses the physical component of the particle, its size, its shape, density, surface roughness, and more. And once we know all of these, we can calculate the comminution age. Now, the fractional loss factor is one of the most important things in this equation because it determines two things. Firstly, it determines the depletion rate. Okay, so here you can see an example of 3 types of particles, okay, large particles, sand particles, medium silt, and fine silt. So in the sand particles, we don't see depletion, right? It stays at secular equilibrium, and we can't date it, right, because it stays the same. Medium silt, you see there is a certain decrease, and much bigger decrease in fine silt, because the F alpha is larger. Because we said if it's a smaller particle, the F alpha will be bigger, larger. And the second thing, it will determine the new steady state value that the sample will reach to. So if the F alpha is 0.1, the new steady state value will be 0.9. Okay, make sense? Okay, so we need to determine this factor, right? So the initial compositions, we set it to be not 1, but slightly higher than 1, because as I mentioned before, not a lot, but substantial amount of our samples are above 1. And we think this has something to do with eutygenic clays that may have been precipitated in those desiccated lakes and depression that we talked about before. And they may have isotopic composition slightly higher than 1. And the F alpha factor, we based it on the same Chinese silicate less that we talked about before, because they did measure it, and it's a very tricky thing to measure. And so we have overlapping samples before, so we use their F alpha value. And now we calculated the ages, right? So we have here the ages, the transport time of dust in the Levant region. And that's the first time that I think this happens. And this is the isotopic composition. And again, we can divide it, we can see how the different provenances behave. So we have the ages of about 100,000 years to Saharan sources, and up to 200,000 years to Arabian Peninsula or local sources. And we have one sample, this one, with very old age. It came from the distant Arabian Peninsula, specifically this one, it came from very far, and it has age for up to 400,000 years. So this is the result of the first chapter, the main result. And to sum it up, we saw that the chemical fingerprint of sequentially leached mineral phases in atmospheric dust revealed the multidimensional provenance of the sample. So that's what the chemical composition that we talked about. And we constrained the transport time of dust in the Sahara Levant region to up to 200,000 years. And now from the air, we move into the sea, and we're going to talk about similar things in marine sinking particles in the Gulf of Aqaba. So you already know some things about the Gulf of Aqaba, so let's see what happens under the water. And we have steep, in addition to all of what we talked about before, we have very steep bathymetry. Okay, we have essentially no shelf on the western and eastern banks, but there is a narrow shelf in the North Beach of the Gulf of Aqaba. And it's highly oligotrophic, and there is strong seasonality. So there is a very strong stratification in the summer and mixing in the winter. And regarding lithogenic input, so other than dust that we talked about before, most of the sediments that enter the Gulf of Aqaba come from the Kinet Canal here in the North Beach, which drain the entire Arava Valley and more. And most of the sediment enter through there and eventually settle on this narrow shelf and eventually makes its way to the center and to Station A, where we did our research. Now, previous research found three end members based on mineralogical composition of organic end member in the shallow water and two heterogeneous end members. And in our study focused on a time series between 2015 and 19. And here you can see the stratification and mixing I talked about. So this is summer stratification, winter mixing, stratification, mixing. And we have also the dust record, which we talked about before. You can see the frequent dust storms. And at the heart of this research, there is a sediment traps mooring array, which I think everybody here know what it is, but I'll say it anyway. So it's basically you have an anchor with a cable attached to it with all kinds of instruments along the cable. In our case, we have about every 100 meters a sediment trap, which we'll see in a moment what it is, and other instruments. And we have at 400 meters depth, we have rotating sediment traps, which allow us, this is how it looks like. So basically it's a funnel with a rotating plate. And this allows us to sample on a daily resolution bulk flux and also other analysis. But the main component of this chapter is 6 profiles of sediment traps that are all along the water column. And basically it's a cylinder that is blocked on the bottom and collect everything that falls into it. And we have 6 of those along this time series. And each one of those is we did sequential leaching and chemical and uranium analysis similar to chapter 1. And other than seasonality and dust storms that we saw, we also noticed another pattern, and that of significant winter fluxes. If you look at the orange line, the 400 meters rotating trap, you see that every time at the beginning of winter and the onset of stratification, we see increased flux at 400 meters depth. Okay, sometimes it's more intense or less intense, but it happens almost every winter. And if we closely examine 2 of these profiles, so this is the August, October versus February profile. So let's start with the summer profile. You can see that the water stratified at about 100 or 200 meters. Okay, the bulk flux, this black line is pretty homogeneous, maybe a little bit higher at the top and the bottom. But if we look at the winter profile, we see that water mixing reached 400, 500 meters depth. And if you look at the bulk flux, you see that in the bottom tracks, okay, these ones, there is 3, 4, 5 times more flux than the summer profiles, and it's not supported from above, right? It's coming from the side or from the bottom, but you don't see it in the upper flux. So what does it mean? To understand what does it mean, first thing we did this very simple mass balance model to understand what are the main components of the flux in our region, and that's POC that we measured. Lithogenic flux, which is based on the aluminum concentration in the silicate phase, in the lithogenic phase, and calcium carbonate based on calcium concentration in the calcium carbonate phase. And when combine all of these, you have a model flux versus the measured flux, and there is decent agreement between the model and the results, with slightly underestimation at intermediate depth, okay, all of these, and that's probably due to mineral phases that we didn't took into account in the model, like iron manganese oxides, which are harder to model their weight and their mass and their flux, because they're very, there is high variability in these phases. And after we did that, we can look at the enrichment factors, which you already know what it is. So we have enrichment factor of the calcium carbonate and the silicate phase, where the pluses signs are the dust, the composition of dust from the previous chapter. And you can see that there is similarity in the trends between dust and marine particles in the carbonate and silicate phases, but there is also differences. And again, to further analyze this, we did PCA analysis. And these are the result of the PCA. This is dust and the marine particles, where the color is the depth. And first you can see there is difference, right, between in the chemical composition between dust and marine particles. And the second thing we noticed is there's also difference between the different profiles themselves. So these are, for example, profile with a high dust load and high surface POC versus profile with enhanced bottom flux. In the silicate phase, it's the same. There is more overlap between the dust and the marine particles, but again, we see this distinction between a profile with enhanced bottom flux and high dust load. When we look at the uranium isotopic composition, we see also differences between profiles. And for example, this is the dust. Whenever we had dust sample that was in the same time as the profile, you can see it here of the different phases. And what we see firstly in the carbonate phases, we see that it's enriched above 1. Okay, it ranges somewhere between 1 and 1.148, which is not surprising because it's marine skeletons, that animals that build their skeleton from the water. But if you look at the silicate phase, we have in a profile with intense dust storm, we see that the signal of the dust, okay, was transferred into the water column, to the entire water column, okay? And that's, by the way, the same dust sample that we talked about before, which ages about 400,000 years. But if we look at these profiles, where the enhanced bottom flux, the winter flux, it's very early January, we see that in the lower sample, there is a highly depleted value of uranium composition, okay, up to even 0.75. Okay, in the dust, I told you 0.91 was low. So here we have 0.75. And here you can see the difference in the silicate composition. So we have a POC versus bulk flux, where the color represents the isotopic composition, and the size of the symbol is the depth. So deep, shallow. Okay, and we have here distinction again between two end members: a shallow end member with high isotopic composition, similar to dust, and high POC. This is this. And we have deep end member with depleted isotopic composition and high bulk flux. Now, before I continue, it's important to understand that the fact that the deep sample have more depleted value, it's not because of the time that passed when the particle was sinking in the water. Okay, the time scale for particle to sink in the Gulf of Aqaba, it's days to weeks maybe, and the difference in the isotopic composition between this and this, it's hundreds of thousands of years. So it's not a process that happened from here to here, but rather two end members. And we use the we use the highly depleted value of the lowest sample, which is 0.75, to determine the F alpha and calculate transport time or comminution age. So this is the isotopic composition and time, and this is the comminution age model based on F alpha of 0.25. And when we put our samples on it, we can see that the shallow end member have ages of up to 150,000 years, similar to dust, and the deep end member have million years or more its age. And this gap of hundreds of thousands of years, what it represents, it's the deposition time of these particles, either in the Arava or the Negev or in the Sahara before they arrive to the Gulf of Aqaba, or the time that they spend circulating in the Gulf of Aqaba since they entered on the North Beach. In either way, this we have in this kind of time scale, we have to take into account another process which causes depletion in isotopic composition, and that's weathering or chemical weathering. Chemical weathering, what it does, it causes preferential leaching of uranium-234 over uranium-238. So we have another process which causes depletion in the isotopic composition, and when we incorporated weathering into our models, we get younger ages. Now, it's not so significant for the shallow sample, so the ages turn from 150 to 100,000 years, but in the deep samples, it goes from million years or more to about 500,000 years. And in any case, we have a very big gap between the two, and that's represent the processes that these samples have undergone in between. And again, it's a constraint on the transport time of particles in the Gulf of Aqaba. So we saw in chapter 2 that different chemical and uranium isotopic fingerprints of sinking marine particles in different phases have different end members. And we constrain the transport time of sinking particles to about 100 or 150,000 years for the shallow end members, and 500 to up to million years or more in the deep end member. And I'll sum up these two chapters, and I don't know if we'll have time to talk a little bit about the third, maybe not. But we saw different mineral phases of dust and sinking marine particles, and they have a clear provenance chemical fingerprint. We constrain the transport time of dust to about 200,000 years and up to 400,000 years. And we constrain the transport time of marine particles in the Gulf of Aqaba to the shallow and deep end members. That's it for the, okay, sorry. The take-home message from this part is that the uranium decay series is a useful tool to constrain the transport time and cycling of particles in natural samples. And we can use this approach to quantify and study global biogeochemical cycles in the ocean. And it's a very nice tool, and I want to also use it here in the Eastern Mediterranean. And that's it. And thank you. If you have any questions, it would be, sorry. If you have questions, I can answer, and if not, I can continue to talk about the third chapter if you want to.
I have a question.
Yeah.
When you were talking about deep, you mean deep sediment traps?
Yes.
So I don't understand why do the deep sediment traps have a different source, because you are talking about a similar time frame.
Yeah, I'll find the
few years of dust storms, but you see that in the deep sediment traps you have a different source.
Exactly.
It should be similar. No, what is the reason that you will have a different sediment source in the deeper part?
So what we think is that sediment arrive here, and then they settle on the shelf and the slope. And when you have deep mixing in the winter, we think it might cause some internal wave. And because we see it mostly when the thermocline decreases sharply.
Yeah.
And then we think it might kind of like cause, like you do with your fin. So it's resuspense sediment from the margins, and then they reach the.
Yeah. You can prove it relatively easy by looking at the micropaleontology and to see what is the source of your shells.
That's true.
Because we did it with turbidites, and of course turbidites is a different mechanism, but it also shows that
I don't know
transport on the seabed.
On the seabed, but the question if those fossils reach the 400 meters trap, because I think it's mostly very fine particles. Yeah.
Yeah. Well, yeah. I don't know.
Yes, but maybe I can look at the work of Natalie on
Yeah,
for
exactly.
check it. Yeah, that's
because she also worked on sediment
on sediment
traps.
traps. Yeah. I look into it. Yeah.
Yeah.
I mean, I'm gonna now after you said it, I'm gonna look into it.
Okay. Yeah.
Yeah.
Can I ask something?
Yeah. Bob?
Just curiosity. There's a paper on Saharan dust versus the Nile dust, fine and coarse particle, and using strontium, lead, I think India, fuel elements, and I wanted to ask how this uranium rhodium here plays a role compared to those isotopes, and if it complements or not, or
So, like I think I showed it before, that most of the work on dust, the using of isotopes is mostly to understand the provenance. So they use mostly neodymium and strontium isotope. Lead, I think it's mostly to see anthropogenic versus natural contribution. And the uranium, the convolution age model, it allows you to constrain time frame. So not the geographic and spatial distribution, but the time that it took process to happen. So it's, you look at the same sample, but you ask different questions.
what do you mean by time?
What?
What do you mean by time?
So that's what I showed you. We constrain the transport time of dust. So instead of saying, I know exactly where this dust came from because I looked at strontium and neodymium isotope. By the way, we tried to look at neodymium isotope from this sample also. Just analytically, it wasn't possible. But it's just answering different questions. The best thing to do is to measure everything on the same dust, and then you know everything about it, but it's not always possible. It's answered the question?
So strontium and neodymium, it's because the samples were too small?
Yes, it's few milligrams divided to 5 phases, and you have to do columns of uranium. And then we tried, we checked it. It wasn't sensitive enough. The instrument.
Move to sediment.
No, in sediment it's not a problem. Yes.
More questions? Well,
Thank you.
thank you again.
Thank
Yeah.
you.
That's it. I don't know.
So,